G'day Year 10s, welcome back to exercise 3J, looking at exponential equations. In 3I we looked at how to solve exponential equations using our knowledge of our index laws and powers of different numbers. 3J is looking at what do these look like when we graph them. When we put them on a graph, what do they look like? How do we know we can do this? Well, if I've got two variables, I can represent it in a two-dimensional. If there's a mathematical relationship between them, I can represent it on the Cartesian plane. And this is something we want to do. So what are exponential relations? Just a quick reminder of what they actually are. Exponential equations or relations are the ones where x is in the exponent. Sounds obvious now, doesn't it? X is in the exponent, hence exponent IAL relations. So y equals 2 to the power of x, 0.4 to the power of x, 3 times 1.1 to the power of x. They're all got something in common there. They all have x in the exponent, in the index. That's what makes an exponential equation. These equations have asymptotes. What is an asymptote? Definition in the book here says a line that a curve approaches by getting closer and closer to it, but never reaching it. Almost true, but there are a few exceptions. I've got one over here in Desmos to show you, just to give you an idea that sometimes there are things that we talk about where our definition changes after time. This is an exponential equation being multiplied by a trig function. Oh my goodness, I know. What's happening as I go closer and closer to the right? This equation is still approaching an asymptote as x gets larger, as x approaches infinity. This function, the value of the function is approaching 0. You can see if I zoom out further, it's getting 0, 0. If I go the other way, it's approaching positive and negative infinity all at once. It's diverging. But on the right, it's converging. So probably a better definition of an asymptote is a value that the function approaches and converges towards. In this particular case with our exponential functions, it will in fact get closer and closer but never reach. If we consider this one 2 to the power of x, what happens as x becomes more negative? Let's have a look at a few values. I need to get my pen back out. That would help. So 2 to the power of negative 5. Well, we know our index laws, that's 1 over 2 to the power of 5, so that's 1 over 32. If I go 2 to the power of negative 10, you're probably still with me on this one. 1 over 2 to the power of 10, 1 over 1024. What about 2 to the negative 50? 50, 1 over 2 to the power of 50. That's equal to 1 over approximately 1.0 times 10 to the 15 there. I don't even know if it's 0.0. Let's go to one significant figure there. 1 times 10 to the 15. 1 divided by 1 times 10 to the 15. A really tiny thing, isn't it? Because I've taken 1 and I've broken it up into so many pieces. Each bit is so small it's effectively 0. That's what's happening as we go along the curve there towards 0. It's approaching 0. And in that case, it will never touch it because with exponential functions, you've always got something being divided. As long as you've got something being divided, there will always be at least a little bit there. So that definition will work for now. Simple exponential equations are in the form a to the power of x, and not being multiplied by this 3 or anything complicated. Couple of things to remember. A has to be greater than 0. Okay, well that makes sense. Negative numbers being raised to powers, well, they're going to flip between positives and negatives. How do I do fractional powers for a negative number? Square roots of negatives, that's not in our real number system. So we've got to have positive numbers for the base in this expression, a to the power of x. And it can't equal 1. What would happen if a equaled 1? 1 to the power of x. Oh yeah, flat line at y equals 1. Not very exciting. The Y-Intercept is always 1. Why is that? Well, where are we when we've got a Y-Intercept? When we have a Y-Intercept, x equals 0. What's my index law for a to the power of 0? My stylus not wanting to behave. My index law for a to the power of 0? That's right, you've already thought about it. A to the power of 0 is 1. So it makes sense that the intercept is going to be 1. We're going to look at reflections, both in the x-axis and the y-axis. And they talk about them there, but I think it's easier for us to have a look at them in Desmos. So let's get Desmos up again. We'll get rid of that equation, as exciting as it was. Zoom in a little bit. Let's have a look at this function, y equals a to the power of x. I'll make it curve a little bit less steeply. It doesn't really matter. 2.3 to the power of x. There you go. Well, that's got that sort of shape. This is exponential growth. You've heard about exponential growth. You've heard about that with COVID-19, of course. So this is with a growth factor of 2.3, growing very quickly. what would happen, well, let's have a look first of all. What happens if that number in A, in the position of A, so at the moment it's 2.3, as I increase it, what's going to happen? I'm going to have a large number being raised to a power. It's going to grow more quickly. So we should see growing more quickly. What does that correlate to in the graph? A steeper gradient. And it's definitely getting steeper there, isn't it? The intercept, it's still at 1. That hasn't changed. But it gets steeper as the base number increases. It's less steep as that base number decreases. If we get it down to close to 1, you can see it's actually growing quite slowly there. That's going up by 10% each time x increases. So changing the value of A changes the steepness, doesn't change where that intercept is. That intercept is always going to be at 1 there. What happens when I want to reflect this? If I want to take all of my y coordinates and make them negative, so everything at the top of the graph, I want to flip it in that x-axis, reflect it in that x-axis, and have it turn up down below. Let's think about a couple of points and see what would happen. So in this particular case, if I look at the point where x equals 5, well, that's close enough. It's about 1.6-ish there. So 1.1 to the power of 5 is about 1.6. If I think about reflecting that point in the x-axis, the x-coordinate's not going to change, is it? Reflecting it straight down here, I'm still on the position where x equals 5. It's the y-coordinate, instead of being at positive 1.611, it's going to be negative. This point here where x is 0, instead of being at 1, I would want to reflect it and have it down here at negative 1. Effectively, my x-coordinates are staying the same, and the y-coordinates are becoming the negative of what they used to be. So if you think about this expression here, y equals a to the power of x, if I want each y-coordinate to be negative, sticking a minus sign in front of that would make it negative, wouldn't it? And I've got that down here, y equals negative a to the x. And you can see that it's a bit annoying that it's in the same colour. Let's give it a different colour. That's the one I want. Make it in green. Hopefully you can see the difference there. I can even turn on projector mode, make the lines a little bit thicker. That might help us as well. So you can see there, y equals a to the power of x, in this case 1.1 to the power of x. It's growing steadily, exponentially growing from left to right. If I want to reflect it in the x-axis, it's the y values that change. So I want the negative of what they used to be. So it's reflecting the x-axis. How do I do that? I put a negative in front of it. We also talked that we want to reflect in the y-axis. We want everything on the right-hand side to go to the left and everything on the left to go on the right. Don't know how that looks in the camera. Hopefully it works okay and they adjust it so that it looks the same. Let's have a think about what's going to happen. This point here, we'll be looking at the point 5 before. Let's put in x equals 5 so we can actually see that point again. It was about 1.61, wasn't it? Yep, 5 and 1.611. So if I want that point to go over here, well, I'm going to need the negative of the x, but I want the y value to stay the same. So I want just the x to be negative. So in the expression a to the x, I want the x to correspond to what the negative of it used to be. So that's where I do y equals a to the negative x. The y coordinate will stay the same, but the x will be negative. Let's have a look and see if that does indeed give us a reflection. And now if I put in x equals negative 5, we're going to see that that height stayed the same. So that point that was over here at 5 and 1.611 is now at negative 5, 1.611. So every x is now corresponding to the negative in its place. The point that used to be at negative 5, 0.621, that's going to be over here now at 5 and 0.621 if I could. Oh, there you go, close enough. So to reflect in the x-axis, the y values are the ones that change, so I put a negative in front of the whole lot because my expression is y equals, so putting a negative in front of whatever it equals is effectively giving me the negative of the y value. If I want to reflect it in the y-axis, the y values are going to stay at the same height. It's the x values that correspond to the negative ones, so you put a negative in front of the x. Alright, let's get back to our OneNote. Oh, I'm getting lost over here. Alright, there we go. So we've talked about the reflections. To find the intersection of a simple exponential and a horizontal line, use the method of substitution, equate the powers. That's what we did in 3i. So we've got y equals 2x, and I want to know where y equals 16. 16 is 2 to the power of 4, therefore x equals 4. We did that already. Some worked examples, sketching the graphs. What happens here as the value of A changes from 2 to 3 to 4. Well, we've already looked at that in the Desmos, haven't we? I just got rid of Desmos, but we probably want to get it back again. And look, I've even prepared them. Here's 2 to the power of x. Let's get rid of those other ones. 2 to the power of x, yep. 3 to the power of x, it's going to increase more quickly. Oh, look at that, it's steeper. 4 to the power of x, steeper again, right? Absolutely. What are the easy points to plot? We always know this first value. You know that it's going to be 0 and 1. We already established that. The other point I would be plotting is let's let x equal 1. So if I turn on that graph again, x equals 1, you're going to see what are the different intercepts there. That's better. 1, 2, 1, 3, 1, 4. Oh, well that makes sense, doesn't it? 2 to the power of 1, that's going to be 2. 3 to the power of 1, it's going to be 3. 4 to the power of 1, it's going to be 4. So the 2 points you can always plot for these, it's very hard to plot accurately outside those 2 points, but those 2 points are always easy to plot. The y-intercept is going to be at 0 and 1. When x equals 1, we're just going to get whatever the base value is, in this case 2 or 3 or 4. Pretty easy to sketch those. So if I was sketching them over here, I'd be going like this. There's my value of 1. Here's when x equals 1. And if I'm doing 2 to the power of x, that's going through the point 1, 2. 3 to the power of x goes through that point there, and it's going to go through 1, 3. It's going to be a little bit higher. Down here, dividing by 3 happens more quickly than dividing by 2, so it goes below the blue line there. 4 to the power of x, you've guessed it, it's going to go through 1, 4. And we're going to have a steeper line again. And that's the way they're going to proceed. Nothing totally controversial about that at all. They've got a couple there for you to try. 2 to the power of x and 5 to the power of x. I think you can picture it. You probably don't need to draw it. We're going to keep going. Sketching these on the same. So 3 to the x, negative 3 to the x. That's probably worth thinking about these again. Let's have a go. So y equals 3 to the power of x. Oh, that's my skinny pen again. 3 to the power of x. I know that point is at 1. And when x equals 1, y equals 3. Well, my scaling's a bit out there, isn't it? We'll get there eventually. 3 to the power of x. Let's make it look at least a little bit steeper. So there's 1. When x equals 1, y equals 3. So we've got a couple of points there that we know. Negative 3 to the power of x. Let's go for a different colour. Well, each y value that I used to have is now the negative of that value. So how does that work? Oh, well, where it was 1, it's now negative 1. Where it was 3, it's now negative 3. And you guessed it, we've got a reflection of that black line in the x-axis. With all of these, of course, you're going to label your axes. Unfortunately, OneNote isn't advanced enough to do that for me. Lucky last, let's have a go at another one here. Red will do fine. 3 to the negative x. What's the difference in the expression? Ah, that's right. Every x has changed to be negative x. That's the negative of what it used to be. So where that x was 1, the same point now corresponds to where x is negative 1. Well, 0 and the negative of 0 doesn't change. So that's where we're getting 3 to the negative x. Give yourself a challenge. What do you think y equals negative 3 to the negative x is going to look like? Well, I've got a reflection in the y-axis and a reflection in the x-axis. Does it matter which order I do it in? In this case, probably not. Down there, then reflect it the other way. I'm going to end up like that. Or if I went to the red one first and then to the green one reflecting in the x-axis, yeah, I'd still get that. So you can play around with these. These reflections are going to be very important as we move on in maths. Transforming graphs is a big part of what we do. Hopefully that will help you out a little bit. Lucky last, find the intersection of these graphs. Well, that's something you can do straightforwardly. We've already looked at that, haven't we? Y equals 2 to the power of x and y equals 8. Yes, I could use a graphics calculator, sketch them and find where they're equal, but I can also just use algebra and substitution. 2 to the x equals 8. 2 to the x equals 2 to the power of 3. Therefore, x equals 3. I'm conscious this is now just ticked over 15 minutes. That's long enough. Have a think about those. Have a play around on Desmos to get used to them. The questions will actually be fairly straightforward in this. Good luck with your work. Keep up your great work. Sounds like we will be back probably in another week or two for you guys. Looking forward to that. But keep up your great work in the meantime, and we'll see you in the next video. Bye for now.